For hundreds of millions of years, water has been a metabolic battlefield. It looks like a sanctuary, but in shallow, sun-scorched floodplains it becomes a trap. As water warms, a fish's heart beats faster. Muscles demand more oxygen. Cells burn energy faster just to stay alive. But physics enforces a cruel trade-off. As temperature rises, oxygen solubility falls. In water warmed to 30 degrees Celsius, dissolved oxygen can drop below 1 milligram per liter. At those levels, gills can no longer extract enough oxygen to support activity. Most active fish require roughly 3 to 8 milligrams of dissolved oxygen per liter to survive. Below that threshold, the harder a fish works, the faster it suffocates. This environmental vice forced life to find a new reservoir of gas, not on land, but in the air above the surface. Before there were legs, there was a backup tank. Gills evolved first as the ancient machinery of the sea, but they have a fatal weakness. They collapse in air and fail when oxygen disappears from warm water. During the early Devonian, roughly 420 to 400 million years ago, the common ancestor of all bony fishes evolved a new structure. A ventral pouch budded from the foregut, the same embryonic tissue that later forms the human esophagus. This single innovation changed vertebrate history. In some lineages it remained a lung. In others, especially ray fin fishes, it migrated dorsally and specialized into a swim bladder. Developmentally and genetically, these structures are homologous. The best supported interpretation is that lung-like organs came first, and buoyancy bladders evolved later. Lungs were not built for land. They were built for survival in dying water. The species that still carry this ancient solution reveal how air breathing actually works. The African lungfish is the most extreme example. When seasonal waters vanish, the lungfish burrows into mud and secretes a thick mucus cocoon that hardens into a sealed chamber. To an observer, the animal appears dead. Movement stops. The heart slows to roughly 2 beats per minute. Brain activity drops close to zero. But internally, the lungfish executes one of the most radical metabolic shifts known in vertebrates. Without water flow, ammonia would quickly poison the body. Instead of eliminating urea, the lungfish dramatically increases urea production. Plasma urea concentrations rise to hundreds of millimoles, acting as an osmoprotectant that prevents water loss through the cocoon. Ammonia is detoxified via an upregulated ornithinuria cycle. Metabolism collapses to a fraction of normal levels. Muscle proteins are preserved. Organs are stabilized. This state is called estivation. Some individuals have survived in this condition for more than 5 years under laboratory conditions. When rain finally returns, the cocoon dissolves. Oxygen enters the lungs. Circulation resumes. Within minutes, the fish is alive again. Lungfish also possess a circulation system unlike most fish. They have a true double circulation with separate pulmonary and systemic pathways. However, blood flow is flexible. During apnea, most cardiac output bypasses the lungs through the right aortic arch. Breathing air is engaged when needed, not continuously. The lungs are not always first. They are available when the water fails. Beakers and reed fish use a different strategy. They breathe air through paired lungs using active buccal pumping. Air enters through spiracles on the top of the skull and is driven into the lungs by coordinated movements of the mouth and throat. Similar to lungfish and early amphibians, their thick ganoid scales provide armor, not ventilation. Juvenile beakers even possess external gills, a reminder of their ancient lineage. As adults, air breathing becomes increasingly important. They tolerate land exposure well, as long as the skin remains moist, offering a living snapshot of what early air-breathing vertebrates may have resembled. Some fish turn air breathing into raw power. The electric eel is one of them. Despite its name, the electric eel is a knifefish, not a true eel. Most of its oxygen comes from air, absorbed through a densely vascularized lining inside the mouth. The eel must surface regularly to gulp air. Without access to the surface, it suffocates within 15 to 60 minutes depending on temperature and activity. Its gills still exist, but they play a reduced role in oxygen uptake. Instead, they remain essential for carbon dioxide removal, ion regulation, and osmoregulation. Air breathing allows the eel to fuel its electric organs, which can produce discharges exceeding 800 volts. Without oxygen, the electric system fails. Electricity runs on air. A similar strategy fuels giants like the Arapaima, which uses a lung-like swim bladder to reach lengths over 3 meters in oxygen-depleted swamps. Its explosive air gulps can be heard from far away. Other fish developed emergency systems. Some species use gastrointestinal breathing, whether loaches, armored catfish, and certain plecos swallow air into highly vascularized sections of the gut. Oxygen diffuses across the intestinal wall into the bloodstream. This method is inefficient and temporary. Nitrogen buildup limits how long it can be used, but it allows survival in damp mud when water disappears. These fish can appear dry and lifeless, only to revive instantly when returned to water. They are so sensitive to atmospheric pressure changes that they become hyperactive before storms, earning the name weatherfish. Another path involves cranial air chambers. Labyrinth fishes such as bettas, gouramis, and snakeheads possess a suprabronchial labyrinth organ, a folded bony structure lined with blood vessels above the gills. This organ allows efficient extraction of oxygen from air. The bony lattice prevents collapse and increases surface area. Snakeheads can survive out of water for several days. They travel across land using their fins to reach new ponds. Some species even tolerate freezing if air pockets remain. The walking catfish uses a similar chamber to cross roads during monsoon rains. Some fish took air breathing onto land itself. Mudskippers breathe through their skin and fins while storing water in large gill chambers. Their skin is thin and highly vascularized, allowing oxygen to diffuse directly from air. They spend most of their lives out of water. They climb roots. They defend territories. They even blink. The mangrove killifish can survive for over 2 months inside rotting logs, breathing entirely through its skin while waiting for tides to return. Across every one of these experiments, one rule remains unbroken. No living fish has completely lost its gills. Even the most air-dependent species retain them for carbon dioxide removal and ion balance. Oxygen may come from air, but chemistry still depends on water. Human lungs are not new inventions designed for forests or plains. They are modified Devonian survival systems built to keep a fish alive in a sun-baked puddle. We did not leave the water because we were ready for land. We left because we had already mastered the air. Land was never the destination. It was simply the last place left to breathe. If you enjoyed this video, please subscribe, like, and share to see more content like these.